we look at the conformational analysis of 1,2-dihaloalkanes. As an example, we'll take the case of 1,2-dibromoethane. Okay, let that be the representative compound for this class of compounds. Now, 1,2-dibromoethane will be having a bromine and 2 hydrogen attached to the carbon atoms. Similar to our butane. The difference is in N-butane, instead of the Br here, we'll be having CH3 group. Now let us look at the various conformations for this compound. Now this is the Newman projection of the fully eclipsed 1,2-dibromoethane, or the what we call as the syn conformation. On 60-degree rotation, we shall rotate the carbon at the back. On 60-degree rotation, the bromine angle between the bromine and bromine will be dihedral angle between the bromine and bromine will be 60 degree. Okay, and this is sort of a staggered conformation, but then we call this as gauche conformation because the two bulky groups, the angle between the two bulky groups is 60 degree. Okay, now another 60-degree rotation, we arrive at the another eclipsed conformation, but this is called a partially eclipsed or simply eclipsed conformation, wherein the bulky groups are not eclipsing each other. The bromine is eclipsed by hydrogen on the two carbons. Another 60-degree rotation, we again arrive at another staggered conformation, or this is the anti-conformation, wherein all the groups are anti to each other, even the bulky groups. The angle between the two bulky groups is, dihedral angle between the two bulky groups is 180 degree. So the two bromine atoms here are anti to each other, in the anti-periplanar position, and hence this is the anti-conformer. Another 60-degree rotation, we arrive at another eclipsed conformation, similar to the third conformation we have seen. One more 60-degree rotation, we arrive at the gauche conformation again. Okay, this gauche conformation and the second gauche conformation we got are almost like mirror images. Okay, and then one more 60-degree rotation, we complete the full cycle and we arrive at the first conformation, that's the eclipsed syn conformation. So these are the various conformations we come across when we carry out rotation across the CC single bond in 1,2-dibromoethane. Now we need to see which conformer is having the least energy and which is having the most energy. Now, as it is clear from the picture, the eclipsed conformer, that is the syn conformer, will be the least stable, or will be having highest energy, because the two bulky groups are coming together. Right? So these two bulky groups will be coming together and they will be experiencing van der Waals repulsive force. Over that, there will be dipole-dipole interaction also between the CBr bond. Now we'll just look at the energy. How do we explain the energy of the conformer? Now we have the gauche conformation over here and the anti-conformation here. Now in gauche conformation, the two Br, the angle between the two bromine atoms is 60 degree. While in anti-conformation, it is 180 degree. So in anti-conformation, there is no question of van der Waals repulsive force acting over here. That is, these two groups are not going to interact with it. None of the groups are going to interact with each other because they are all placed farther apart. And also in anti-conformation, there is no provision for the dipole-dipole interaction. While in gauche conformation, one destabilizing factor is the repulsive force, that is van der Waals repulsion between the two bulky groups. So steric repulsion is experienced, and then the CBr bond which is present will be polarized, slightly polarized, as I've been telling you. And the carbon will be having a partial positive charge and bromine will be having a partial negative charge, and because of which the dipole-dipole interaction arises. Okay, so in gauge conformation, there will be steric repulsion and dipole-dipole interaction, because of which the energy of the gauge conformer will be increased than the anti-conformer. And in case of eclipsed conformation, the steric repulsion and dipole-dipole interaction will be at its maximum. So when compared to gauge conformation, eclipsed conformation will be having the highest energy. So the stability order, we can say eclipsed conformation will be the least stable, gauge conformation will come next, and the most stable conformer in case of 1,2-dihaloethane or 1,2-dihaloalkanes is the anti-conformer. Alright, so that will be the what is called order of energy order or stability order. So the most stable will be anti-conformer, followed by gauge, and the least stable will be the eclipsed conformer, that is the syn conformer. Between gauge and syn you will get the eclipsed conformer. Here you have this eclipsed conformer, because in this case the two Br are placed farther apart, but then they will be having some amount of energy between, repulsive force acting over here between Br and hydrogen, bromine and hydrogen. Alright, so eclipsed will be the syn conformer will be the least stable among all these conformations. The syn conformation will be the least stable, and the most stable will be the anti-conformation. So, and gauge will be in between the syn and anti, because gauge conformation will be destabilized by steric repulsion and dipole-dipole interaction. Okay, hope it is clear to you. Thank you for listening.